All right. So I'm going to continue with the DNS today. We talked about how DNS allows you to get unique names by using what you call a dotted namespace. So names of the form A.B.C.D.E can be actually as long as 255 names deep. But of course, usually we just use 3 or 4 levels. But we haven't really talked much about how these are used and how it's all put together. So I'm going to spend some amount of time going over that first, and then talk about something called content distribution networks, another acronym, CDN. And content distribution networks actually completely have changed the way in which we use the web or use the internet. When you go to a place like what you think of as Facebook or Google or Yahoo or any large website, you're actually going to a content distribution network, and we'll see how that works. And then if there is enough time, I'll talk more about email and see how that goes. Okay, so let me remind you what the DNS, or the domain name system, what it means, or actually service, not system. Oops. So DNS stands for domain name service. At one level, what it is doing is giving you unique names. And the way we get unique names is by having these registrars. So registrars are people or entities that guarantee uniqueness within a certain subdomain. So we have a registrar called CA, for example, or COM, and so on. And then CA will guarantee that Waterloo is unique. There is no other entity, no other registrar, sub-registrar called Waterloo, etc. And then Waterloo will guarantee that there's nobody else called CS, for example, or ECE, etc. And then you get uniqueness in the whole namespace, which is the set of all possible names, because each one guarantees in its own local area. So what we're doing over here is that we're doing this notion of delegation. Delegation means that you're saying, look, I don't really care what happens under ca.uwaterloo. You can do whatever you want. I've given you that authority. Go create whatever names you want. Just make sure they're unique. And that delegation kind of goes down. So that gives us unique names. So there's something at the top which is called dot or root. And this is the one that's making sure that these top level domains are unique. Okay? And this root is run by a committee. It's called the International Committee on Assigned Names and Numbers. It's called ICANN, another acronym for you, ICANN. And the joke is I cannot, I can't. So they really should have had an apostrophe T at the end of it. But ICANN is the one that assigns top-level domains. So they make sure and this is extremely political, by the way. It's extremely political because think about it. Just now they announced that if you pay $100,000, you can get any top-level domain you want. So you can have, .google if you want. Okay, and Google probably has it, as far as I know. I realize I'm being anti-Google. Okay, I used to be anti-Microsoft, now I'm anti-Google, so it just changes. Anyway, but how many top-level domains should there be, and how can you guarantee the unique, etc. It's all quite political, and it is actually discussed, by governments and so on. But at this point, anyway, all we need to know is that the root guarantees uniqueness. Okay? So I've talked about unique names. Now let's see how it's put together, because this is sort of the design of what it's supposed to be like, but we haven't talked at all about how it's actually done. Okay, so let's see how that works. So the first thing that DNS is giving you, in addition to unique names, that's the first thing. The second thing it's giving you is it's giving you a mapping, and it's giving you a mapping from names to IP addresses. And we want IP addresses because we want names rather than IP addresses, because IP addresses are kind of hard to remember. It's very hard to say, well, I want to go to 129.97.2.4. Most people don't remember what that means. They can say, yeah, I want to go to ns.uwaterloo.ca. That sort of makes sense. It's a name server for uwaterloo.ca. So we want to use names rather than IP addresses. So that's a perfectly reasonable thing to do. The other thing it does is that it allows aliasing. And aliasing means that we're mapping names to names. Okay, so I take one name and they'll say that name actually means some other name. Okay, so there are several reasons why you might want to have aliases. So let me give you an example of this. One example of this might be that I might say that uwaterloo.ca, it maps to www.uwaterloo. Okay, so here is a mapping. Why do you think we might want to have such a mapping? Okay, this name to that name. So you want to go to your browser and type uwaterloo.ca, and in fact what you want to do is sort of behind the scenes, you want to say, look, go to the web server called www1, which in turn is going to be mapping to some IP address. Okay, so you're going to do two mappings. First from some name to another name, and then from the name to an IP address. Okay, now you could be a bit cleverer about this. You could have this mapping. So let's say this one happens. Okay, now let's assume that I'll show you another mapping, and let's see why we would do that. So this is the first reason, because it makes it easier to remember. You just say uwaterloo.ca, you don't need to remember it's www1 is a web server. Let's say that I think I mentioned this last time. Let's say there's a company called Staples, it buys Office Max. So you go to officemax.com, and you just, because that's what you remember, and actually you can translate to staples.com. So what's going on over here, right? This one is pretty straightforward. You have a merger or acquisition, so the old name goes away, but people still remember it. They may have documents which refer to it, right? You may have documents that just go to officemax.com, whatever, and then we want to send them to the other place. So that's a second reason why we may want to do that. A third reason would be this. So I want uwaterloo.ca, and I want to do the following. I want it to map to actually several. Okay, so www, let's say 10, I don't know. I'm returning, when you ask me for uwaterloo.ca, when you ask DNS or uwaterloo.ca, it may return multiple values, let's say 10 of them. What's going on is that then you're free to pick one of them. Okay, so normally what we do is that we pick the first one, like so. So what DNS does is it does what's called round robin. It's going to return you a list of names, and it rotates them each time. So each person, you ask it 2 or 3 times in a row, it will say www1, 2, 3, and then 10, 1, 2, 3, and then 9, 10, 1, 2, and so on. So what happens is that the load that's going to the website is being split across all the different backends. Okay, and you can do this another way as well. You can take this and actually map that to multiple IP addresses as well. So you have 2 ways of doing load balancing. You can go from one to multiple names, and then from names you can go to multiple IPs as well. So you can actually load balance across this. So the load gets spread across. So any name that gets translated to any other name is called aliasing. Okay. So these are some reasons why we may want aliasing. You can probably come up with other reasons as well. At least get 3 good reasons for doing aliasing. Okay. So these ones are referring to specific server names. Okay. And in fact, these names are shared by multiple IP addresses. This happens to be so. If you have just one IP address, then this would be the name of a particular server. And if you have these multiple IP addresses, then all of these IP addresses correspond to one single name, right? So we think of a name as sort of a handle that says, okay, this set of servers all respond to this name, right? So name is sort of an abstract entity at this point. We don't really, and it instantiates, it becomes this IP address. Eventually, you have to have an IP address in the end. But another reason you may want this kind of thing to aliasing might be because you change your name, right? Instead of an acquisition, you just change the name or something, or you move somewhere else. So the names allow you to hide all those moves as well. But you know, okay. So aliases, people understand how that works. So now let's get into how we actually implement this whole bit. So the way the thing is implemented is we have notion of a name server. just like a web server, you have a name server, okay? And essentially what we do is we send it a request and it sends back a response. That's basically all we do for DNS. So we send a request just like we did with the web server. We send a request and we get back a response. And the request says, please give me the mapping for a name, okay? It gives you a name. So I don't have that up there, so I'll just give it to you right over here. So I'm going to give it a name, and it returns back one of three things. Either it says, here's another name or set of names. That's the first response. Like, I give you a name, here's a set of names back. The second response could be, here's a name, I'm going to give you an IP or a set of IP addresses, okay? Or the third thing could be, I don't know what this name is, but you know what? Go to some other name server instead. Okay, and then that name server can help you. Okay, so you kind of hand it off. I don't know. Why would you say I don't know? Because you might go to root and say, or you go to CA and say, I want an address cs.uwaterloo.ca. CA says, I don't know. I handed that off. Go to the name server for uWaterloo. Go ask that guy. And that guy says, I don't know. Go to CS. Right? So we hand it off. And that's how it works, okay? So how are these implemented? The name server actually inside it contains a database. And if you remember, we sort of draw databases like this. So we have a database. And what the database contains is what I call records, which is all database contains records. And we have corresponding these three translations, we have three types of records. This kind of record, which maps from a name to a name, is called a Cname. I'll just explain that in a minute. This is an A and this is an NS. So a Cname record, is this visible from the back from here? So a Cname record is a record which says this name actually maps to some other name. It's an alias. Okay, so www.waterloo.ca actually means www.1.uwaterloo.ca. So C stands for canonical. So what we're saying is that this is an alias for the canonical name this. Okay, and that's why I call it a Cname. So in other words, DNS recognizes the request, the name in the request, as being an alias for a canonical name by looking at the database, and it says, yeah, this actually maps to something else. So the Cname record will look like this. It will just say Cname, uWaterloo.ca, www.1uwaterloo.ca, and that's the Cname record. It's really as simple as that. Just three fields. Actually, there's a couple more fields which I'll come to in a minute. But these are the main fields. Okay? The A record is an address record, and the address record says this name corresponds to this IP or set of IPs. Okay, and that's how we do address records. And the NS record is a name server record, and it says that this this prefix, okay, because you have uwaterloo.ca, so everything that starts with uWaterloo, for example, at the CA name server belongs to some other name server, okay? And what we put over here is actually the name of the name server, not its IP address. And then we have another A record that says the name of the IP name server corresponds to this IP address. And that's just kind of a funny way of doing it, but that's the way they do it. There are some reasons for that. Okay, so if you go to the name server which has a Cname record, you ask uWaterloo.ca, it will come back and say, oh, the real name actually is www.1uwaterloo.ca. Then you go back to it and say, what about give me the record for this? It'll say, okay, that's an A record. But you want to end up with an IP address at the end, correct? Yeah, you want to get, and at the end you need an IP address because otherwise the service interface of the internet says, give me an IP address and send a packet. So you don't know if you don't know the IP address, you can't do it, right? So you need that at the end. DNS blocking would essentially mean that the request carries with it the IP address of the requester, right? If the IP address of the requester is such that a certain name should not be resolved because of blocking. So you may work for a company. Let's say you work for a company, and that company says, during working hours, you're not supposed to watch YouTube. It's a corporate policy. So what would happen is you would try to resolve the name youtube.com because that's the URL. And the request has an IP address that's from inside the corporate network. So the name server would say, oh, that IP address is not allowed to resolve this name. So it's going to come back and say, sorry. Right? So that's DNS blocking. It's pretty straightforward. Okay. So how do we use this name server? So let's go back to this over here. I'm going to use this middle panel. I'm going to leave that up because I'll show you how this works. So the way the system works is like this. So every computer on the internet today, pretty much every endpoint, as we call it, has to be configured with the name of a name server. Okay, you have to put it in. When you get any internet connection, no matter what, if you have a home gateway, if you have a mobile phone, if you have anything, the first thing you're going to do when you start it up is to say, this is my name server, okay? And you can use any name server you want. You're not restricted to using any particular name server. You can use any name server you want, okay? So you take the endpoint and you configure into it by hand the name server. Okay, so that's your entry point into the whole domain name service. Okay, that's your name server, that's your NS. Okay, that's your starting point. Endpoint is anything that is connected to the internet. It could be your desktop, your anything that doesn't have anything more connected to it. Okay, so I'm being vague here because actually there is no definition that's good. Any definition you make of an endpoint actually is not that valid. So I'm going to be deliberately vague because, yeah, okay. Any other questions? So, but think of it as a desktop or a mobile phone. Okay, that's what you get. Where you're running a browser, think of it that as a. You don't run a browser on your router, for example. You don't run it on an access point, right? You run it on the endpoint. Okay, so you go into the name server, and what you're going to do is you're going to send a request over there. This request is exactly these requests over here. All your requests go to the first name server. That's what you're going to do over here. You're going to send to the name server. Okay. Now what this name server is going to do is the following. It's going to first check and see whether it has the resolution already. In other words, this name server has got a local, what's called a cache. Okay. Why does it have a local cache? Because chances are pretty good somebody else asked for it already. You know, if you go to youtube.com, chances are pretty good somebody asked for it, you know, a few minutes ago or a few seconds ago. So it's there in the cache. Why bother, right? And this is a standard thing to do in computer science. In computer systems of all sorts, we always stick a cache because it's cheap. It usually works. And in the worst case, if it's not there, it just adds a tiny bit of delay. But if you have a hit, it's very, very good. So whenever possible, we use a cache. So here we have a cache. It's a name cache. And it says that this name resolves to this IP address. And you just give the reply back. If you don't have it in there, then what this has done is it's configured with the name server of if it has the IP address of the root. Okay. So we configure this. So what is the root? The root is the top of the namespace. Okay, so this knows the name server or the IP address of the name server for all the top level domains. Okay, and so root is kind of the super name server, if you will. Okay, there's this, and there's not one of them. There's 13 of them, which are labeled A through M. In a fit of absolute creativity, they call it A, B, C, D, all the way up to M. Is that 13? I think it is 13. And each of those is actually replicated widely. So A, the root server, I think it's called A, because that's all you need. Is replicated many, many times. B is replicated many times. So it can take a lot of load. So those IP addresses for the root are very, very well known. They're kind of locked down, nailed down. And so this name server is configured with the IP address of all the root. It can go to any root. So typically, it'll pick the closest root to go to. So go to the root and say, okay, let's say we pick a name. I don't know, we'll just say, we'll continue with the CS. Let's say cs101.cs.uWaterloo. Okay, so that's the name that you want to resolve. Okay, and let's say you're somewhere at the other end of the world, you're in Mongolia, and you want to get this thing. So nobody's ever hit that before. It's just completely out. Nobody's never used that. So you don't know what to do. So when you don't know what to do, you go straight to the top. You go to the root and you say, look, I have this name. What do I do? Okay. What the roots are configured with, because they are the registrar, their name server, is that they have the NS record for CA. That's what they have. They have the name server record over here that says, I don't know what the IP address is, but you know what? CA, I delegated that to the Canadian name server. Okay, so it's going to have a record over there, which is going to, so the root is going to be over here, and the root is going to have a record of the form NS, and it will say CA, and then it will say something like names. Typically, name servers are called NS1 or NS2, so NS1.ca perhaps is the name, and then it will have an A record, which will say NS1.ca, and it will give you some IP address, let's say 128.32.6.4, something like that. So the first one says, I don't know what this name is, but you know what? The CA name server is called ns1.ca. It might know better. And by the way, ns1.ca, that's IP address is this. Okay? So everybody get these two lines? So this is the guts of delegation. This is how delegation works. You're taking a name and you're passing it on down to the next level down, which is this. Now what this name server over here does, this is the one in Mongolia, it says, okay, I still don't have an answer, but I got further ahead. I can go to CA now. So it goes and sends a message to ns1.ca. The second one, this is that name server, and says, hey, do you know about cs101.cs.uwaterloo.ca? ns1.ca says, look, I don't know, but you know what? I have a record that says ns, the name server for uwaterloo, okay, .ca, which is the string that you want, is called ns1.uwaterloo.ca. And by the way, that particular name is a record. That IP address is ns1.uwaterloo.ca. And its IP address is 129.97.1. What is it? 129.97. Something, I think. 128.2. I'm just making it up. The first two are correct. I don't know the last two IP addresses. So that's the A record. So, okay, so now you know uwaterloo. We repeat this, right? So this guy goes to this IP address and says, hey, I want cs101.cs. So this one says, I don't know the IP address, but guess what? I have the name server for cs.uwaterloo.ca, and that's its IP address. Go ask it. And when it asks it, it gets the IP address in the end, and then you're done. Look at the beauty of this. Which allows us to do is that no matter where you are in the world, with just three questions, three queries, you're back to getting the answer that you want, no matter where you are. And once you have that IP address, we'll discuss later how routing happens, but you can get to that endpoint no matter where you are. Okay? So the other nice thing about this is that once the delegation is done, the root doesn't really care about what are the names in Canada. It just doesn't care. Any name is fine as long as it's unique. The Canadian registrar, CA, doesn't really care what are the names inside Waterloo. Okay? And all the way down. Okay? CS guarantees the uniqueness of names inside CS, but then it manages it so we have a clean separation of administrative entities. The administrative entity responsible for each entity just keeps its own names clean and responds to queries for the other. So the NS record, so the Cname record, I didn't show you Cname, but there would be a Cname like this, for example. So let's say I want to call cs.uwaterloo.ca, also called computer science. Let's say comp.sci, I can say comp.sci.uwaterloo.ca. .ca is the same as cs.uwaterloo.ca, for example. Let's say I had that Cname record. That just maps an alias from one to the other. Actually, this is not going to be here. It's going to be uwaterloo.ca. This is the wrong location for it. But anyway, this is a Cname mapping. I would change the Cname and make it an A mapping, right? And then that would remove the alias and make it an IP address. This is the response coming back to, right? And I'm going to answer that. For that, I need my high-tech crayon markers, whatever. Okay, so the endpoints are configured with the name server, okay? And that's sort of your go-to person, the go-to server, okay? And that's fine. You don't need to worry about that. What about this guy over here? It turns out that there are kind of two ways in which you can resolve the query. So I've used a new word over here called resolving. Resolution or resolving. And resolution, it means that I'm going from a name to an IP address. Okay, eventually. So I'm giving you a name, and after some, cogitation, some kind of process, you get back an IP address. That's called resolution or resolving a name. So the way the endpoint resolves a name is to go to the configured name server. It goes to the name server, says, resolve this name for me. It does it, right? The way this guy does it, there are two ways of doing it. One is called iterative, and one is called recursive. Iterative, recursive. And this is really complicated names for very simple ideas. The iterative case, what happens is it sends a request to the root, it gets a response back, and then it goes to the next guy over here and gets it back, and then keeps doing it, iterates through it, okay? And that's actually the default. But there is another way of doing it called recursive, where what will happen there, and I'll use the blue for that, is that the name server makes a request to here, and this will make a request on your behalf, and this will make a request to somewhere else on your behalf, and get the reply back, get the reply back, get the reply back, and then the reply back to you. So it kind of goes in deeper and deeper and comes back to you, okay? So that's called the recursive, because you're making a query recursively as opposed to going into the loop, okay? So these are two ways in which you resolve names. So, but in both cases, from this perspective over here, the endpoint to name server, it's a perfectly straightforward thing. You send a name, you get back an IP address, and you're done, okay? And the tool we use to do this, the two tools, one is called dig, the other one is called NSLOOKUP. Okay, and I think in the homework assignment, I've asked you to use dig. NSLOOKUP is an older one, dig is a more recent tool. And with dig and NSLOOKUP, in both cases, you can choose which name server you're going to ask to enter into the name system. So you can use your local name server from Rogers or whoever provides you IP service, ISP, your ISP at home, or from your Waterloo's name server, or you can go to Google's name server, which I believe is this very easy number, 8.8.8.8. I think that's Google's name server, so you can go there, and then you can ask them, all of them, the same questions. And hopefully you should get the same answers from all of them, okay? So, yeah. So this is kind of the high-level view really into DNS. There's a lot of complexity in it, and a lot of complexity arises from actually making it more secure. How do you make sure that some random person doesn't say, oh, I'm scotiabank.ca, give me your data, right? You probably don't want to have that happen. So how do we prevent what we call namespace hijacking, okay? And actually hijacking was very easy to do about 10, 12 years ago, and then there were a bunch of very high-profile hijackings that happened, and just for people to show that, look, it can be done. How can you trust this infrastructure, which is so easy to hijack? And so people have cracked on a bit. It's still not terribly difficult, but it's beyond the means of most random hackers, but it can still be done. It is still done. Okay, and now you see how blocking works. Blocking DNS works, and you can see how we enter into from different name servers. So if some name server is unable to resolve your name, you can just change the name server, and you can resolve your name that way. Right? That's one of the things you can do. So Google's name server is open, and so on. The last thing I want to talk about with name servers before I go on to content distribution networks is this question of scaling, okay? Now, the structure of the name servers at first looks fairly complicated. Why do we have these separate name servers and they talk to each other in this funny way? Because if you were to ask me how to build a simple name server, that's what I would do is to just have a single IP address, like 8.8.8.8, just for the sake of argument. And everybody goes there and gives them the name, and it comes back with an IP address, and that's it. Centralized. You just go there, it gives you the IP address, you're done, right? Like in a web server, we don't have this complicated, handoffs and so on and so forth. You want the homepage for cbc.ca, you go to cbc.ca, it says here's the homepage. If you can translate a request response for the home page in such a simple way, go to cbc.ca, it gives you the home page. Why do we need all this complicated, handing off and this and that and the other? So the answer is that the two things that this is giving you that a single centralized location can't. The first thing it's giving you is local administrative control, okay? If you had a single central name server in the sky at 8.8.8.8, for example, let's say Google runs it, If I wanted to change the IP address for CS101, I've got to go to Google and say, hey, please change this for me. And they say, who are you? Prove that you are in charge of this particular space and the whole bit, right? So it's a pain in the neck. It would never happen. Okay? That's the first thing. The second thing is the load on that central server would be huge, right? It would be very, very difficult to deal with the number of resolutions that are happening, okay? And so we wouldn't want to do that. Okay? Now, as we'll see in a few minutes, I'll talk about how we can use this thing called content distribution networks to spread the load of name servers. And what you'll see is that this idea of taking the load, or taking the central thing and spreading it apart to reduce the load actually is used for the web as well. So even though you think you're going to CBC and getting CBC's web page from one server, you actually are using something that looks more like this than a single central server. Because even that is actually not able to take the load. No single server can take the load. Okay, so that's how we construct these large websites. I had hinted at it. I'll talk more about it when we talk about content distribution networks. A third reason why this we may want to split it up this way is also because of the speed of light. Remember that the pipes, we cannot go faster than speed of light. So if I have a name server which is local to me, which is at the University of Waterloo, I get back responses pretty fast. If this name server is sitting somewhere in the UK, for example, just from speed of light propagation delays, I'm spending about 20 to 30 milliseconds, okay, for each query. And that's much slower. And so it makes sense for me to have a local name server as close to me as possible. Okay? And finally, it turns out, and researchers have studied this, that this cache over here is incredibly important for this whole thing to work. If that cache weren't there, nothing would actually work, okay? Because it's critical that answers are stored over here for some period of time. Okay? So how long is that period of time? That comes from the records. If you remember this, the name, I said there's an extra field over here, that's called the time to live field, TTL. The time to live field means this is how long it's okay for you to retain this resolution. Okay, so I'm going to resolve this name, and then you can keep it for so long, and after that, this is probably not going to be a valid resolution. Throw it away. Okay. We have a time to live explicitly because we know that things may change. Okay, we don't want you to hang on to something that may change, so we have an explicit time to live field. And so the cache is going to actually periodically purge all the records that have expired and then re-get those things. But if the time to live field is fairly long, so typical value is 86400. So can anybody tell me what 86400 is? Sorry? Milliseconds? No, it's not milliseconds. It's a number you should kind of remember, one of these. It's a number like 365. What's 365? Days in a year. What is 86400? Number of seconds in a day. Okay. So 1440 and 86400 are good numbers to remember. 1440 number of minutes in a day, and 86400 is number of seconds in a day. These are things someday you might need to use it. So 86400 is a good number to know. And that's the number of seconds. So we give the expiry time in seconds, and it says keep it for a day and then throw it out. And that caching is what's going on over here. And every level actually caches and does it. And okay, so there's some issues with this, but I'll let that be for now. Because this is hopefully giving you a big picture of how DNS works, why we need it, what it does, and how you would go about setting it up. No, the time to live expires, and then they refresh it. So the authoritative name server, so I didn't talk about authoritative name server, the name server that for sure knows what the value is called authoritative name server. The authoritative name server is the one where you make the change, right? That would be, for example, the authoritative name server for this is CS, or do you want with CA, knows for sure what CS 101 is. They know for sure. Everybody else has just got a copy of it. Okay, so they have non-authoritative answers. But the authoritative answer is this. So if you get a non-authoritative answer, you can go and ask for an authoritative answer if you want, if you probe them deeply enough. Most people don't. Most things are configured to not do that because that would break the system. It would have too much load on it. So I guess to answer your question, Tommy, you could force an authoritative answer, okay, but that's not what you would normally do. Any other questions? Okay, so good. So you know more about names than most people at this point, which is good. And now we're going to switch gears and talk about content distribution network. So by the way, all this is an application on the internet. At the bottom, all we have at the bottom is just pipes connecting endpoints, right? We have pipe from here to here, and then there's all the stuff that happens on top. So it's an application layer protocol that implements name resolution. So that's what DNS is in a nutshell. Okay, so the reason I want to talk about DNS first, and now I'm going to CDN, is because CDNs use these ideas for websites as well. So I'll first tell you what a CDN does, the service, and then I'll tell you how we implement it using two different approaches. And that probably will take most of the time. If you have some time, I'll talk about email. Okay. Oh, I guess I need to take a break. Let's look at content distribution networks. So the purpose of a content distribution network is to distribute quote-unquote content. What is content? It's websites, it's images, it's audio, movies, video, whatever. We don't really care what the content is. We're completely agnostic to that. But let's start by taking sort of the simplest case. Let's say that you come up with a video distribution service. Let's call it, say, YouTube. And this was, in fact, the way it started was a couple of guys were sitting around in San Francisco, I believe, and they said, we want to upload pictures of each other or videos of each other, at the zoo. They went to the zoo and they took a picture, and I believe Chad Hurley is the guy who started it, one of the guys who started it, and he was standing in front of the elephant enclosure, and they took a picture of him, a video of him, and they wanted to upload it somewhere, and they found it was hard to do. So they said, okay, let's just call it YouTube, we'll just put it there, and they did. They put the video there. And so from our perspective, what is it? It's a web server. And then behind it, there's a database or a disk which contains the video. And you send a request to it saying, I want the request for some video ID, some ID. And then you get back the response, which is that video. And then you play it, and that's basically it. That's how YouTube started, with the one video of one guy standing in front of one elephant. And now they get, I believe, 40 hours of video a second, or 40 hours of video a minute, or something like that, something crazy. So, okay. How do we scale it up, right? This is the same exact problem we had with the DNS, the centralized DNS. I have one big kind of server in the sky, and everybody in the world wants to upload and download from it. So how do you do it? A single server isn't going to do it. And so we go back to our DNS thing and say, okay, let's be clever about it. What we're going to do is that we're going to actually have many web servers that all pretend to be the web server, okay? And so we're going to take this content and we're going to put it into many, many different endpoints, like so, and all over the world. And then what you're going to do is we're going to push these copies of it out to all of these places. And then when somebody asks for YouTube, you actually don't go to the single web server in the sky, you go to one of these guys over here. And then you get it from there. But from your perspective, you didn't know the difference. Okay? So everybody got that? Okay, so we have a couple of questions right away, which is that do we make copies of everything? I mean, YouTube has a ton of data. Do we make copies of everything or not, right? Where are these going to be located? And how do we fool people into thinking that they're going to the central location over here when they're actually over here? Okay? So the answers are all over the map, depending on how it's actually done. But I'm going to first give you the example of how YouTube does it, and then I'll talk about how Akamai does it. So YouTube is a proprietary content distribution network. That means Google owns everything. It's not a business that says, I'm going to host it for you, whatever. It's Google owns everything. So it makes life somewhat easier, and then we'll go into the more complicated case in a little bit. So the first question is, do we replicate everything? Okay. So what do you think? Do you need to replicate everything or not? Bonus access. So let's say somebody makes a request which you don't have. What do? Get it the long way, put it in your cache, and then give it over here. Voila. Thank you. So everybody else, did you hear our answer? Right? In all your suggestions, you were thinking too much about who wants what. You're thinking, oh, China, they don't want English. The company won't allow it. Or I can't replicate everything. No. Let the people tell you what they want by making a request. If you don't have it, you say, hang on, you fetch it, you make a copy, and you give it. Remember I said you use this cache everywhere. Cache is what's going to save you in every system, okay? That's exactly what's happening over here. As the requests come in, this cache is going to fill up with exactly the content that people are asking for. If they don't ask for it, it's not going to be there. It's magic, it just works, right? And when the cache fills up, which it will, we just throw away the ones that aren't being used the most, we call it the least recently used video, you just throw it away. Because guess what? If somebody wants it later on, you just pick it up anyway. This has the master copy right here. So this form of replication on demand is called pull replication. Okay, I still haven't told you how to fool people into thinking this is YouTube. In fact, it'll just take a minute to show you how to do that. But the replication over here is on demand, and we don't need to think too much about what's going on over there. We just put up the cache, and you say, go for it, and it just gets filled up with the content. So the web server, the cache in China will be full of Chinese videos automatically or automagically, right? And all the cache in here is going to be filled up with the local content, etc. Just because that's where the requests are going. But we need to make sure that the requests from a local geographical area all go to the same local thing. If Chinese requests could go all over to all the different maps, all the different caches, we'd be in trouble. We need to geographically route them to the closest one, and I'll show you how to do that in just a minute, okay? Any questions about this so far? So that's the pull type. The push type is actually also done, and it's done based on popularity. So if I know something is popular or going to be popular, more precisely, I can just push it out, in advance. So think of the New York Times, for example, or Globe and Mail. Every morning they have a newspaper, 3 in the morning or something, they have a new newspaper. They know in the morning everybody's going to go read it. Instead of waiting for people to pull it, you can push it out in the morning, and then when people go there, it's already there. So you can have both push and pull for content distribution, and that's what's actually done, right? The beauty of this is what? It scales, right? You have more load, just stick in more servers with more cache, and it just keeps growing. There's no limit to it. That's why YouTube grows like crazy, because there's no limit. There's no need to. You have more traffic, you have more ads, you have more money, you have more servers, you put it in, and it keeps growing, you get more money, and so you just keep making money, more and more money, basically. Okay? As long as people are willing to look at ads or whatever, people are willing to advertise, it keeps growing. Yes. Who decides the push? The content owner typically decides what to push and when to push based on previous, that's like a gut decision, like this is going to be popular, okay? And they know that new content is being created, it's going to push out. But, if you get a service from Akamai, okay, Akamai will tell you what do you want to push, you tell them what to push, they'll push it for you. But this is a proprietary thing, remember? We don't have a service yet. Yeah, they could imagine that something that's popular, let's say over there, we should push it to everybody because we think it's going to go viral and everybody will want it. That's there is no like math or something, it's kind of gut feeling, this is what you think is going to be popular. Nobody knows what's going to be popular. Pull works magically, but push, you have to think about it, and we don't have good ideas with this. Okay, let me move on over here because I want to tell you about how the last little bit, which is how to make sure that people go here instead of there. So let's say this is Canada, and I want everybody in Canada to go to this particular cache of YouTube, okay? So how do we do it? The way it's done is what's called request routing. And what I mean by request routing is that this particular thing is an IP address over here. Let's call that IP A. Okay, that means the IP address of that cache over there. And let's say this thing over here is IP B. So what we want is that if you are going to ask for YouTube in Waterloo, for example, you're going to be given IP A, but if you ask for it, let's say in New York State, you're going to IP B, which is going to somewhere in New York City, right? We want to have that kind of separation. So we want to route the request for DNS resolution exactly in this way. So the way we do it is in kind of a couple of, the way it's done is like this. You're going to ask for youtube.com to be resolved, right? So youtube.com has a DNS server over here. So this is the DNS server or name server. Which is sitting somewhere, okay? When you make a request to this name server, let's use this for the orange. So you ask for youtube.com from your browser. And this was going to be directed by DNS to YouTube's name server, which is over there. So it goes here. Now you have some source IP address. Oops. You have source IP address, which is the IP address you came from. And what YouTube has, it has another database, this orange database, which is basically IP to location mapping. Okay, and as you'll find out from your homework assignment, there are very good maps which from your IP can locate you down to about 5-10 kilometers. Okay, so if you go to geocodeip.com, they will actually show you on the map where you are within a few kilometers, okay, from the IP address. We have these maps already. So this says, hey, that's a Canadian one. You know what? I'm going to resolve it to IPA. And then you're going to go to IPA for your YouTube content, and you're going to get back stuff from the cache, which is what Canadian people are watching, and you'll get kind of what's popular in Canada. On the other hand, if you're calling it from somewhere else, let's say this is IP C over here. The IP address is C for this particular server, and you're out over here. When you go over here, your source is something else. This is source 2, and this one says, oh yeah, that IP maps to this location, so you're going to send back the resolution for this one, and you're going to go here and get it back from there. So by geographically coding the source IP addresses and using DNS, just IP name resolution on DNS, I can split it up. I can be smarter than that, and I can actually have a bunch of servers, not just one, but a whole bunch of servers, all with different IP addresses, all serving content, okay, using load balancing. And so when you get this request over here, I'm going to send you one of these 10 or 100 servers, okay, which all correspond to Canada, for example, and then you will get the data from there. Okay, and so we get the load balancing and the geographical locality by using this approach over here. Any questions about this over here? So the whole magic is this thing over here. And I won't tell you how that's done, but we have these tables today. Okay, so that gets everything worked just right. This whole process happens correct, except that your local name server, once it resolves it, will kind of cache that YouTube means IPA. So you'll kind of be sent there anyway. You don't need to go back each time. But yeah, it's really mapping from your local name server to that. Right? And if you change the name server on Dig, for example, and you look for YouTube, you'll find you'll get different IP addresses corresponding to where you asked from. Okay, so this is how YouTube works basically. Okay, I mean, yes, they send video content in Flash format and all that, but that's sort of not really important from my perspective. What YouTube is doing is to use the DNS idea, but just spread it out like so. And this is what Facebook does. This is how Facebook works as well. Facebook has, so if you see something called FBCDN, now you know what that stands for, right? What's FBCDN? Facebook Content Distribution Network. Those are the names of all those nodes over there. Right? Okay. Now, This is a proprietary CDN, and I explained to you basically this concept of pull and push and the idea of caching and geographical coding and how that's done. If we have a commercial entity like Akamai or Limelight, I think it's called Limelight, and Cotendo, these are commercial providers of content distribution. They have a slightly different way of doing things. So I'll just tell you what Akamai does because they were the first and sort of most popular service. So the first approach of, and what I'm talking about is how to route requests. So the first one is what's called Akamization. And this is what's used by, for example, Yahoo uses Akamization. And what happens is this. So I'm going to redraw this because this is the same thing is going to happen, but you'll see that there's a slightly different relationship. So we have over here sort of Yahoo, which has its website, and it has some server which has the true content, and we'll call this the origin server. And then over here we have Akamai CDN, which is the content distribution network, and it has lots and lots and lots of endpoints. About 70,000 endpoints, okay? It's not 25, 30, it's 70,000 endpoints. So it's really all over the world, it's all over the place. So we have somebody over here who's a requester, and the requester is basically asking for some content, which is typically, Yahoo uses it for all the images, okay? All the images come from Akamai. So in Yahoo, in the origin server, we have the home page, which is the HTML page. And in the HTML page, we have some images like so, right? What Yahoo wants is that when you ask for the home page, you want to get the home page from here, okay? Why? Because Yahoo wants to know, what ads are being served to you and wants to know where you're going to, all sorts of stuff that it really wants to track you, okay? So it wants the cookies to go there, for example. In the other case, the cookies are going to the YouTube caches. They're not going to the main YouTube, but that's okay. They're all onto the same thing, so everything is going to be tracked, internally. Here, we want the origin to be involved for the first HTML page. However, what Akamization does is that these over here, the image tag, which refers to some URL, is going to have the Akamai's name on it. Okay, instead of Yahoo, it will have Akamai's name. So instead of saying, typically an image tag will look like this, yahoo.com/image/image1. Instead, it will say akamai.com/image1. Okay, it's actually a little bit more complicated than that, but roughly that's what it is. So the URL for the image tag, we write it down, so say yahoo.com/image/image1. It's going to say actually something like yahoo.akamai.com/image/image1, a JPEG. And if you go to Yahoo's homepage and you just do view source, you'll actually see this, okay? And this is now a name, right? This thing over here is a name, and so that's going to go into DNS, right? And so this request is going to get back to you that URL. So your browser is going to make a request to DNS, your name server, saying, hey, what is this yahoo.akamai.com? Okay, I don't know what it is. Tell me what it is so I can go ask for that image. That yahoo.akamai.com is going to be sent by COM to Akamai's name server. And Akamai's name server is going to say, oh, that's a request for Yahoo. And what's more, I have a geocode database that tells me where you came from. So I'm going to send you to this guy over here, my local Akamai cache, to get that image, okay? How can I do that? Exactly the way as before. Because once you get into this, it's exactly like YouTube saying, oh yeah, I know where you are, I'm going to send you here. Same exact deal, Akamai sending you here. And then after that, you get the local cache, etc. And it just works. Okay, so what's happened is, however, that this HTML has got to be modified, and what Akamai does is it gives a tool to Yahoo. You run the tool on the HTML, it spits out these translations, and then you're done. I'm not doing anything with aliasing over here. This is purely rewriting the HTML. Rewriting the HTML from this to this, so that now when you go try to resolve this name over here, it's going to go to Akamai. It's not automatically. We're changing the image tags over here, right, in the HTML. We're actually rewriting the image tag. Oh. Yeah. So that's the first way of doing it. That's Akamization. So how to do one's Akamization? We want to change the image tag. The second way of doing it is actually pretty easy, and it's basically called, I don't know what I think it's called Cname Aliasing. I don't think it has a name actually. And what you do here is that this is kind of a sneakier way perhaps, but what happens in this case is that we will have the images.yahoo.com /img image1. Let's say this is the URL in the image tag in HTML, okay? That means go to the server called images.yahoo.com and pick up this, okay? What we can do is this. We can add a Cname record that says Cname, which says images.yahoo.com is actually yahoo.akamai.com. Okay, so let's see what's going on here. So you make a request to Yahoo, and it gives you back HTML page. Okay, now nothing has been modified. It looks like straight old HTML, except that it has, instead of saying yahoo.com/image, it says images.yahoo.com/image/image1.jpg, right? That's in the HTML, right? Then you say, oh, I don't know images.yahoo.com. So what should it be? So you go to Yahoo's name server, and Yahoo's name server says, oh, you know images.yahoo.com? Actually, it's an alias. It actually means yahoo.akamai.com. So then you go to yahoo.akamai.com, and yahoo.akamai.com says, oh, you are coming from here. I'm going to point you to there, and then you're done, right? So here we don't even need to change the HTML. It's going to be done this way. And this is the other way of getting. So once Akamai gets a DNS request from anybody, after that they have complete control of where to send it. They can send it here, there, anywhere, simply by resolving it. And what Akamai does as a business is to keep track of the loads on each of their endpoints and the content there and where it's coming from, and based on that, they send the request to the right place, and that's basically what people are paying for. It's on Yahoo's name server, correct? That's what the Yahoo name server. So this record is sitting in Yahoo's DNS, Yahoo's DNS. So that's the way using CNames to do this kind of problem. So what are the advantages of doing this? Okay, so let's think about it. First, anybody who gets Akamai service or CDN service can spread the load among 70,000 different endpoints. Same thing with YouTube or Facebook, right? You have lots and lots, so it scales forever. Second, let's say somebody's trying to do a denial of service attack. They're launching lots and lots of requests onto Yahoo. It doesn't matter. They're all going to be sent to these endpoints, and there's tons of them. So basically, Akamai has shown, and other CDN providers have shown, that you can't do a denial of service attack because there's 70,000 endpoints. Which one are you going to attack, right? And if they're being attacked, they'll just switch you to somebody else. So they can prevent denial of service attacks. The third thing is these things are close by. So the round trip time, the speed of light propagation delay is fairly low, so you get requests a bit faster, okay? And they can also do push as well as pull, as you saw earlier. So for all these reasons, content distribution networks are kind of the way to go for any large website. So anything that's going to be growing, you probably end up using a content distribution network. And that's the structure of the internet. That's the way that we build large websites today. Okay, we're out of time, so I'm not going to talk about email. Next class is Andre. He's going to talk about peer-to-peer networks, BitTorrent and Skype and data centers. Okay.